Welcome to this lesson on searching and sorting. A common application that your programs will need to do when you work with arrays is to search the array for a specific value or to sort the array into ascending or descending order. In this lesson, you'll learn how to write your own sorting algorithms. You'll also learn that the C library provides a very powerful searching and sorting algorithms that you can put to immediate use. So let's go ahead and get started. In this first program, we declare an array of integer values and initialize the array to the values 30, 10, 40, 20, and 50. We then use a for loop to loop through the array elements. With each iteration of the loop, we check to see if the current array element is equal to 20. If it is, we display the message found 20 at the array index. Let's go ahead and run this program. And sure enough, it found the value 20 at array index 3. In a similar way, this program declares an array of character strings and initializes it to AAA, CCC, DDD, BBB, and EEE. The program then uses a for loop to loop through the elements of the array, looking for the string BBB. To find the string, the program uses the strcomp function that's defined in the header file, string.h. Let's go ahead and run this program. And again, the program found the character string at index 3. And so in this case, our programs did the for loops and did the searching themselves. Often though, we'll want to create a function that does searching. And we can create a function that searches integer values, maybe one that searches floating point values, character string values. We'll see that the comparison function differs a little bit. And then we'll also see how the C runtime library provides functions that can help us. In the previous program, we performed a sequential or linear search to find our values, meaning we started at the first item in the array and we looked at the first one, then looked at the second one, looked at the third one, until we finally found the value or we reached the end of our array. A binary search is appropriate when your data is already in sorted order. So you can think of a binary search as the way that you search a dictionary. You're looking for a particular word, so you open the dictionary, normally to the middle, and you say, nope, I've gone too far. So you take half the dictionary and you open that part to the middle. And you say, oh, haven't looked back far enough. And you take that part of the dictionary and you divide it in half until you find your word. And the binary search works kind of the same way. We're going to take our array of values and we're going to look in the middle first and say, is this the value we want? Yes, great. If not, is it higher or lower than the value that we want? And then we'll look in the middle of that list and we'll look in the middle of that list until we finally find our value. So this program defines a function called binary search that receives an array of integer values and also the value we're searching for, as well as the array size. It's going to use a variable called found that will set to 1 if it finds the value, and then it's going to use variables called high and low and mid that's going to define kind of that region that we're looking for within the dictionary. Our high end, which would mean, are we looking at the start of the dictionary to the middle? That would mean our low is 0 and our high is the middle. And the mid value is going to be kind of that halfway value in between our high and low. And it's going to continually repeat, looking at a value, saying, is it higher or lower? Give me a new region to look in. Is it higher or lower? Give me a new region to look in. And it will do that until it finally works its way down to the value that we're looking for. And so when we run this program, we're going to create an array of values from 0 to 100, and then we're going to search for different values and display the locations where we found them. And so sure enough, it found that location, or the value 27, at 27, which it should. We had an array of values 0 to 100. It looked for the value 500 and didn't find it, so it returned the index value of -1, telling us the value is not found. But to better understand the processing that's performed, I've included in the source code that you have a printf statement that's commented out So with each iteration of the loop, you can see what is it looking at for the low value, the mid value, and the high value. So you can see how it's mimicking our dictionary search. To help you perform search operations, the C library provides the LSearch function. And the LSearch function is powerful because we can use it to search arrays of different types. So we don't need a special function for integers and another one for floating point, but instead we can pass pointers to our structures and to our actual comparison functions. And so to use LSearch, you need to create a function that's going to work with pointers to the values and return an integer value. And if the values are equal, it will return 0. If the first value to be compared is bigger than the second, it will return a positive. If the second value is bigger, it will return a negative. And so all of our comparison functions will work in this way. So you can see that in compare, I return the value of the first value minus the second. So if they're equal, it will be 0. If the first value is bigger, then it will be a positive value returned. If the first value is smaller, it will be a negative value returned. The LSearch function is going to use this function to compare values. That's how we're able to use LSearch for different types of data. We can create a similar compare function for a floating point, a similar compare function for a type double, a similar compare function for a character string array, and we can sort them appropriately. Within main, I declare my array values 5 and I initialize it to some values 44, 69, 3, 17, and 23. I specify the size of my array is 5. The value that I'm looking to find is 17. And I'm going to declare a pointer to type int that's going to get assigned a value, the pointer to that value within the array, or it's going to be null if the pointer is not found. And now I'm going to call the function. And so depending on the type of array I'm using, I'm going to cast my result to a pointer of that type. In this case, I've got an integer array, so I'm using a pointer to the type integer value. I'm then passing by address the value that I want to find, my array, by address the number of elements, the size of the data type that I'm working with ints, and then I've got a pointer to a function that's going to do my compare. And so in this case, I'm passing a pointer to that compare function I created earlier, and the LSearch is going to use that pointer function. And we look at them, pointer functions, in our lesson on pointers. And so you'll want to go back and look at it because they can be a little confusing as you're first getting started. When we run this program, we see that the value 17 was found at offset 3, and sure enough, there it is. And so using the LSearch function, we can search a wide range of array types using the same code. All we need to do is pass a different function to perform our comparison of the values. We've learned that a binary search is faster than a linear search because it's going to cut in half with each iteration the number of elements that we have to look at. And it turns out to help us create a binary search, the standard C library provides the bsearch function. And it too, like the LSearch function, is going to receive a function to a pointer that does its comparison. And so in this case, it gets a function that's going to return an integer value that if the values are equal, 0, negative if the first value is less, or positive if the first value is greater. And so in this case, I'm returning the first value minus the second value. That gives me a 0, a -1, or negative or a positive. Within my main program, I'm defining my array of values and initializing them to 51, 60, 78, 79, 93. I'm then declaring a pointer that will get the pointer location of the value that I'm looking for, and then I'm looking for the value 78. I call the bsearch function and I cast its return value to a pointer to an integer. And I pass to the function the value I want to find, my array of values, the number of elements in my array, the size of my array type, it's type int, and then my comparison function. And so if they find the value, it's going to return a pointer to it. Otherwise, it's going to return null. So if I run this program, it quickly tells me that value 78 is at index offset 2, which it is. So using the bsearch function, I can search different types of arrays using the same code. So I could search a floating point, I could search a integer. I just need to define a comparison function that can compare those types of values. We talked about the fact that a common operation is to sort the values of your array, either in ascending order or descending order. One of the simplest sort routines is a bubble sort. And it's so named because with each iteration, it's going to kind of bubble the largest value to the top, and then with the next iteration, the next largest value, and then the next largest value, and the next largest value, until we finally get our array in sorted order. There's kind of a picture of it here. The bubble sort is good for arrays that are probably 30 elements or less. Beyond that, you want to use a different sorting technique. And so I've defined here a bubble sort routine that gets an integer array and the size of the array. And to bubble the values to the top, it's going to use two index variables and a nested for loop. And so it's going to look at a value at a time and then keep track of the values that's already bubbled to the top. And so we'll walk through the code here in a second. But within our main, we're declaring an integer array of 30 values. We're then using a for loop to give the array random values. And so I get a long value returned by the rand function. I'm using the modulo operator just to take the remainder so I can get a smaller value. And then I'm doing a sort of the values. I'm passing the array and the number of items it contains. And then after that, I'm looping to display the array contents. So when I run this program, you can see my values are sorted from lowest to highest. Let's look at the bubble sort function for a second. And so when we find two elements that are out of order, so if a array sub I is less than a array sub j, we need to exchange the values. To do that, we use a temporary variable, and we put the value of array sub I into it, because in our next line we're going to overwrite the value of array sub I with array sub j. So we can do that, and then we put into array sub j the value of the temporary variable that we stored. And so that's how we do our value swap when two values are out of order. The selection sort is another sorting algorithm that's fairly effective for small size arrays. And essentially, the sort begins by selecting the top element. And it's then going to compare that top element to every other element in the array and exchanging it as necessary. And so by the time we finish the first iteration, the top element will be good. We'll select the second element and compare it to each one of the elements. And we'll repeat this process until we've gone through all the elements in our arrays in correct order. And so this code implements the selection sort. Again, it gets passed an array of values and the size of the array. And it's got a temp variable that we can use during our swap, the current variable that we're looking at, and then an index variable that allows us to compare the current value to all the other elements in the array. Again, when we find an element that's out of order, we assign it to temp, and then we update the array element, and then we assign the second array element the value that we put in temp. And so this program does the same thing. It gets random values for 30 array members, and then calls the sort. If we run this program, we see our arrays, or our values in lowest to highest order. The shell sort is named after Donald Shell, who invented it. It sorts an array by starting with a gap distance, which is typically the midpoint of the array. So if we have an 8-item array, we start with a gap of 4. And we're going to loop through our array, comparing items at that gap of 4 until we don't have any exchanges. When we don't have any exchanges, we then divide our gap in by 2. And so in this case, we'd have a gap of 2. And we're going to look through the array until we don't have any exchanges. Then we'll divide it by to again now give us a gap of 1, and we'll loop through the array with a gap of 1 until we don't have any exchanges. When we find a value that's out of order, we do our swap and we set the variable exchange occurred to 1 so that we know that we had an exchange with that gap. The main program creates 50 random values and then calls the shell sort. So when we run our program, we see our values ordered from lowest to highest. And the shell sort is again pretty good for arrays or 50 elements or less. Beyond that, we want to use the quick sort. So the quick sort works by essentially breaking the array into 2 lists. And it grabs a midpoint value and it puts items that are less than or equal to that midpoint in one list and items that are greater than in the second list. And then it calls itself with each list and does the process again. Grabs a midpoint value, puts items in a list that are smaller and items in a list that are bigger, and then it calls itself again with each one of those lists. And so it's a recursive sorting algorithm, and eventually we get down to the point where we've got our array in sorted order. And so I've given you code here for the quicksort algorithm, and it's fairly complicated, and you want to put some printf statements in it. In my algorithms course, I talk about the functioning in detail that's going on. In this case, we're just going to illustrate what's going on in main and then look at the qsort routine, which is provided by the C standard library, because it's more functional in that we can use it for all array types. And so within main, we're creating an array of 100 values, and quicksort's the sorting algorithm to use once your array is bigger than 50. It's going to have the best performance. And we're calling quicksort to sort the array, and then we're printing the values in sorted order. And just that fast, it returns them. So quicksort's always going to be fast. For small arrays, you can get away with using the bubble sort or the shelf sort or the selection sort. But for big arrays, you want to use the quicksort. And so we're not always going to be sorting arrays of integers. We may need to sort an array of character strings, for example. So I've given you a bubble sort here that's capable of sorting an array of character strings. And it uses the strcomp function that's built into the C standard library to compare the strings. And if they're out of order, it saves pointers to the strings. So it saves the lesser value in temp, and then assigns the other value into that value, and then reassigns the value in temp. So we swap the variable values. And so within main, we define an array of character string pointers and give it some initial values, and then we call the bubble sort to sort those, and we display them. When we run the program, we see our array values in correct order from lowest to highest. And so our sort's very similar. We're just going to go through and compare items and bubble up the largest one, and then do the next iteration and bubble up the next one. And each time we find an item out of order, we just swap it. And so despite the fact that we're using character strings, really the only thing that differs is rather than comparing two numbers, we're using the strcomp function to do our comparison. And so to help us sort arrays, the C library provides the qsort function. And it's very powerful in that we can use it to support integer arrays, floating point arrays, character string arrays, and we can do that all in the same program. So we don't need separate functions to do it. All we need to do is define our comparison functions. And so in this case, I've defined a function that compares two integers. And so it's going to return 0 if they're equal, a negative if the first value is less, or a positive if the first value is greater. I'm doing the same thing for a floating point compare. I'm returning a negative value if one's less, a 0 if they're equal, and 1 if the first value is bigger. And then for my string compare, I'm calling string comp, which does that same thing, 0 if they're equal, minus 1 if string 1 is less, and 1 if string 2 is greater. And so I'm then creating in my main program a myriad of arrays. I've got an integer array, I've got a floating point array, I've got an array of character strings, and you can see I'm using the same qsort function to sort values despite the types. And the only thing that's really differing is I'm telling QSort how big is my data item and which function should I use to compare them. And QSort's using a pointer to a function behind the scenes to call the correct comparison. And so if we run this program, we see our integers sorted correctly, our floating points sorted correctly, and our character strings sorted correctly. And we did that using just the QSort routine. And so the tricky part about QSort is learning how to use a pointer to a function. But once you've done that, you've got a very powerful sorting routine at your disposal. And so the previous program used QSort to sort arrays of int and float and character string from smallest to highest. There may be times where you want to go in descending order from highest to lowest. To do so, you just need to kind of reverse the logic of your compare functions. And so I've done that here. And so you can take time to compare the two programs, and you'll see that all I did was swap the order of some variables. And so when we run this program, it shows my integer values in descending order, my floating point in descending order, and my character strings in descending order. And so the rest of my program maintained the same. And so QSort's extremely functional. Arrays let our program store multiple values of the same type. The problem with using arrays is that your programs must know in advance the number of elements the array is going to store. In the next lesson, you'll learn how to allocate memory dynamically as the program executes, and how to use memory to create linked lists, binary trees, and other data structures that can grow or shrink as your program's needs require.